Good afternoon, and welcome to the WuSci Neurosciences Institute Symposium Fire Chat. We don't have a fire, but we will nevertheless have a chat. I'm your host. I'm Tony Weiss-Corey, the director of the NIDE Initiative for Brain Resilience and professor of neurology here. And I'm honored to welcome our guest, Carol Ho, who's Chief Medical Officer at Denali Therapeutics, and she's also Head of Development. So what we're going to do is first have a discussion about how to potentially tackle and develop treatments for neurodegenerative diseases for the first 20 minutes or so, and then open up the floor for discussion. But first, let me tell you a little bit about Carol and give her a warm welcome.
Thank you. Great to be here, Tony.
So Carol got her medical training at Cornell University. She did residency at Harvard University, and then came out to the West Coast, where she did a postdoctoral training in actually basic neuroscience with Marc Tessier-Lavigne. She also did clinical work in the Department of Neurology, where she was an instructor and faculty, and then moved with Marc to Genentech. She did a brief stint at Johnson & Johnson, I believe, and then came back to Genentech and rose through the ranks there, became Vice President of Early Clinical Development before she moved to Denali in 2015, and where she has really done an absolutely amazing job and led to the clinical development of, I think, 8 programs now, from the early and initial drug designation to even late-stage development at this point. So it's really an honor to have you here. But let's get started with the discussion. And maybe one of the first questions that actually came up during our amazing presentations and also in the question and answering is this question about how do we tackle these neurodegenerative diseases that are so prevalent. It's estimated that about 30% or so at age 85 have Alzheimer's disease, suffer from cognitive impairment, and that rises dramatically as people get older. But it has been incredibly difficult to tackle these diseases. And so maybe first a personal question, Carol. You had trained first sort of clinical medicine and then went to basic research. What motivated you to tackle this incredibly difficult problem and go to industry and try to do it there?
Yeah, well, so thanks, Tony, first of all, for the warm welcome and introduction. And it's so great to be back at Stanford and see everybody here today. So, you know, the question of neuroscience and how I went into it is a really good one. I was an undergrad at Harvard in biochemistry, and I steered clear of neuroscience because I thought it was too complicated to understand, and I couldn't see how that understanding in those days, this is in the early 1990s, that would actually translate into a therapy. It just seemed very complicated at that point. So I never thought I would go into neurology. And when I went to medical school, I actually had plans to become a surgeon. I felt like the problems were very clear. It was very clear how to fix them, and you could see patient benefit, and that was the goal. And actually, my first year of third year medical school, I did a neurology rotation, and I was really just completely moved by what I saw. And I think what I saw that was different in neurology patients is that it wasn't just the patient that was suffering. The families were really suffering because in many cases, the patient that they brought in or were seeing with their loved one in the hospitals, in the clinics, were almost an entirely different person from themselves. And that concept just really stuck in my mind and made me feel like that I needed to do something about that. And so it entirely changed my trajectory of my third year of medical school. I did my surgery rotation. I loved it. Didn't go into surgery. Partly I couldn't hack the sleep deprivation, but I think more than that, it was that I was just really, I felt like that it was a life goal to make a difference for these families. And so in that, it really was a turning point in my decision also to really go back to basic science with the plan of trying to understand more about neuroscience before trying to pursue drug development. And so in that decision to pursue neurology, I knew after I finished my residency training, I would go back to do basic science work with the goal of really trying to understand the diseases better to make a difference for development of therapeutics.
Great, yeah. So I personally have been working in this space for 25 years or so. And so like many of us, as we get older, our parents get older, got affected personally by this disease. And you know, my dad is now 92. He's forgetful, clearly early stage Alzheimer's. And you know, if my mom asks me, so you know, what are the options? What are the treatments? I feel we still don't have. I don't have an answer. So did we make any progress?
Yeah, it's a great question, and I think the field has been characterized more by disappointments than successes, but I think we've made a tremendous amount of progress. And if you look at other diseases where maybe the science was a little bit more advanced back in, you know, the early 90s as I was thinking about trying to understand these diseases, I think we see that it requires really a stepwise process. And you know, it starts from understanding basic biologic pathways that are important, understanding more about those pathways and how we can measure them in animal models, understanding then how we can translate that into the clinic. And there's a huge jump from going from animal models to the clinic. And I know this is something that, you know, was discussed a lot this morning around understanding these basic mechanisms of memory to understand how you can impact this in the clinic. But just in terms of if I look back at where I was when I made that decision to go into neurology and why I was not interested in that as an undergrad is there was so little known. So if you think about Alzheimer's disease, for example, what we knew about Alzheimer's disease was largely related to the pathology that had been seen by Alzheimer himself, who identified the disease, and looking at things like amyloid and tau and lipid accumulation. These were things that people saw in pathology that really there was no understanding around the time course of those things and clinical disease. And one of the things we always talked about in medical school is, hey, you know, you see all this amyloid in pathology samples, but some of these patients, you know, died cognitively intact. So what is that relationship between those protein aggregates and clinical outcomes? And I would say that I think there really has been an enormous amount of progress just in even understanding that. And that comes from really multifunctional groups working together, public-private partnerships to understand the trajectory of the disease over time. And some of these initiatives, for example, the Alzheimer's Disease Neuroimaging Initiative that looked at clinical data, the biomarker data with new imaging technology that allows you to visualize amyloid and tau, enabled us to understand the trajectory of the disease. Now, that doesn't give us a therapy, but you can imagine the challenges of drug development. If you don't even know what the natural trajectory of the disease is, it's very, very difficult to impact it. So I think that already, that the sort of the relationships between clinical outcomes, imaging outcomes, and timeline are a huge impact in terms of how we think about developing therapies. I think the other revolution that I see over the last 20 years has been genetics. And you know, I think when we think about major changes in the environment, I think the cost of genetic sequencing decreasing by a couple of orders of magnitude really led to a lot of GWAS discoveries of new genetic pathways that may be of importance in disease. Now, I think maybe I'll just stop there for a minute, because going from a genetic risk or determination of disease and how that really plays out biologically is there's still a big expanse of trying to understand that, and then on top of that then trying to identify medicinal material that can target those pathways and then try to understand the dose that then goes into patients. That's very complex and it takes time. But what I see is that we have made progress, even in our failed studies, of learning about the disease, learning about what we can modify, learning about what doesn't work. And all of that is, I think, going to contribute to our ability to have a success, I'm hoping, in the next decade.
Right, yeah. And maybe coming back to this, sort of this concept of how we tackle these diseases, you mentioned Alzheimer's, And I think it's across multiple neurodegenerative diseases. We started obviously with clinical manifestations, then having the opportunity to look at the brains of some of these patients who died, and identifying these molecular hallmarks of the disease in Alzheimer's disease. It's amyloid plaques and tangles, and then figuring out whether there are any genetic basis for these. And right, it was really a revolution when people discovered these very small numbers of patients who had autosomal dominant mutations in the amyloid precursor protein, in presenilin, and that was associated with an early onset Alzheimer's disease with a pathological picture and a clinical manifestation very similar to what we see in these, older people that get what we call sporadic disease. But this came up earlier, in a question, I think, to Beth Mormino's talk from Nicole, I believe, what is really the role of these amyloid deposits? Is it the same that we see in the autosomal dominant forms of the disease? Because the field has really taken this link and said, okay, here is nature tells us this is the cause of the disease, so it must be relevant, if not the cause, but highly relevant for the later age onset diseases. How do you see that?
Yeah, so I think there's been a lot of evolution, and even we can talk about a little bit data even in the last few weeks that I think potentially address this question of the amyloid hypothesis. But maybe just from a historical perspective, we knew in sporadic Alzheimer's disease that you see amyloid in pathology, and actually some of these autosomal dominant families that have Alzheimer's disease that is driven by these mutations that cause overproduction of amyloid. It was actually not known even in the mid-1990s when I was in medical school that those were actually Alzheimer's disease. In fact, the large Colombian family with the E280A mutation that's due to presenilin 1 mutation, it wasn't clear what they had. In fact, some people thought that it was a form of mental retardation. And it wasn't until actually looking at the pathology that it was observed that the pathology was the same. You saw this amyloid, you saw this tau buildup, and the pathology looked almost identical to sporadic Alzheimer's disease. And then really understanding the function of presenilin 1 and its role in amyloid processing really linked the two together, that there is a genetic driver that, at least in these autosomal dominant families, was sufficient to cause disease. So in these families, it's an autosomal dominant, and almost all of the patients who have that mutation end up going on to have Alzheimer's disease, and very close to the onset timing of their relatives. So I think that those observations really drove, I think, additional enthusiasm in this area, that the amyloid hypothesis was genetically driven. And then there's some additional data in an Icelandic population where there appeared to be a protective mutation as well in APP, and that suggested that the genetic hypothesis, there was further strength to that genetic hypothesis. So this has resulted in obviously an enormous investment in this pathway for treatment of Alzheimer's disease that I think has been very controversial, and it has been a long and winding course. But maybe I'll just make a few observations from the molecules that first went into clinical development and the ones that are in development now. And I think maybe it'll speak to even some of the challenges in drug development. I mean, one really interesting observation is if you look at the first anti-amyloid compound that went into clinical development, bapineuzumab, it was dosed at as low as 0.5 mg per kg quarterly, every 3 months in patients that were ApoE4. Now the dose levels, it's 10 mg per kg every other week. So I think one thing just to point out, and I think this is about sort of the evolution of our understanding, there's a lot that's been understood from failures, and this dose question is a major question that I think is a challenge in neuroscience, in a large part because it's very hard to access, in many cases impossible to actually access the brain to make sure that your drug is actually hitting the target and is having the intended biologic consequence. The closest we can get is imaging, which is really important, and the technology there is developing. And then CSF, getting CSF is almost the closest that we can get into the brain. And that's where I think there have been a lot of developments in biomarkers to be able to measure these analytes to have more confidence that we're having the intended effects on the biology. So I think it's a long-winded answer to your question, but do I think that we have made the right decision as an industry and as a community to focus on amyloid? I think the jury's still out on that, but I think that the genetic data really supports that investment. But it's not the only pathway that I think we need to think about. And I think as we think about brain health and brain fitness in general, there are probably going to be multiple pathways that are going to be important. And my view is that, one of these pathways, if successful, can tell us a lot about the disease that will enable other therapeutics in development. It'll tell us that we can intervene at a particular time in disease. That's been a big question. When do you start treating? Do you start treating from a prevention perspective? Do you start treating when someone first has symptoms? Or, and I think it's not popular to wait, obviously, until you're really symptomatic. And that just, what we've learned is that we see lots of failures in more advanced stage disease where we don't think that we can reverse the pathologic consequence of these processes. And so I think there's a lot that we can learn, again, from early data from these programs that may look positive, that tell us that we're on the right track.
Mm-hmm. It seems certainly a logical decision to target these pathologies, and as you said, it takes such a long time to then actually test an idea in humans. Maybe you can tell us a little bit. There was just maybe a blip of good news potentially with a clinical trial that met primary and secondary and points that looks again promising for targeting amyloid in the disease.
Yeah, so after multiple failures in the last few weeks, a drug that's developed by Eisai, partnered with Biogen, reported positive top-line results for lecanemab, which is an anti-amyloid therapy, which again, the dose is much higher than was used in previous therapeutics targeting amyloid. And they've reported top-line, very statistically significant positive results, a p-value of 0.00005 on the primary endpoint, which was CDR sum of the boxes, plus secondary endpoints that include the endpoints that have been used in other programs in developing anti-amyloid therapies and have been used for other therapies that have been in development for Alzheimer's for symptomatic therapy. And that's the ADAS-Cog and the ADL scale. So the reason that I mention those endpoints, and when I want to answer your question and provide some optimism about progress, even those endpoints and being able to measure changes in a therapy that has a disease-modifying effect, those I think have been uncertain. So a lot of those endpoints were developed actually for symptomatic therapy when patients are much more advanced in their disease, and I think that has been an open question. Now, if this data pans out and is really robust and real, it will be presented at a scientific conference at the end of November. It takes out a lot of the variables that we have when we think about and design late-stage clinical studies, where I think unlike in the laboratory and in preclinical work, you can do an experiment multiple times. It really is challenging that you get to do this experiment once or twice, and you have a lot of variables that have to be addressed. And so, in my mind, any improvement is actually progress in the field. Now, I think there will be debates around clinical meaningfulness, a 27% reduction in progression of these endpoints. I think that's a question. Is that clinically meaningful? I think there's a lot we still don't understand about clinical meaningfulness in disease-modifying therapies. What does it mean if you reduce something by 30% now, but that continues during the course and the evolution of the disease? That may be very different than symptomatic therapies, where if you have a 30% improvement over 6 months, that may help you for 6 months, but it doesn't have really as a durable long-term impact, which is what we really want for patients and caregivers and families.
Yeah, I think it's also important to, even if the amyloid antibodies don't work out, if one looks back how this idea even came about. I remember when Dale Schenk, out of a small biotech startup here in the Bay Area, first presented data in an animal model that produces amyloid deposits based on these genetic autosomal dominant mutations, and he immunized these mice with amyloid fibrils. That was a totally crazy idea, and people laughed at him and said, why would you be able to immunize against a protein that accumulates in the brain? That will never work. First of all, there's a blood-brain barrier, and the antibodies will not go in. 15, 20 years later, most of the major modalities to treat neurodegenerative disease, or not most, but a large number, uses this strategy to deliver antibodies into the brain. Sometimes with so-called brain shuttles, where you try to further improve the uptake of antibodies. But I think it has also brought immunology and neuroscience together, and people start to look much more on, is there actually a role for antibodies even for T cells in the disease? So I think that has certainly changed, I think, in my view, the approach. But it brings us also back to using models of the disease. And when Dale did these experiments, they used, as I mentioned, APP transgenic mice. Now people use more advanced models where they just introduce in a humanized form sometimes of the protein, the mutation, or even just in the endogenous protein they introduce a mutation, or the human A-beta sequence. And they develop, interestingly, amyloid deposits and cognitive impairment that are somewhat reminiscent of what you see in people. But what's your take there? And how does Denali approach using these animal models, which obviously were not very informative, and one can say they led to a lot of waste of money and failed clinical trials, but I think that's sort of unfair in my view. What's your position?
Yeah, absolutely. So I think that the challenge of modeling a very complex human disease in animals is, I think, obvious. And I think as we think about, what are the opportunities to learn something from animal models and how can we use this? I think that's, again, an example of something we've learned. And we've learned because of failures. We know now that animal model data, for example, Morris water maze, is not really predictive of what happens in the human clinical condition. But I think the models are still really important for the point that I brought up earlier around dose and trying to understand the dose relationship with pharmacodynamic effects that you can model in animals. And in animal models, you can actually access the brain and look at things to determine whether you're having the intended consequences that you're looking for. And so the approach that we've taken at Denali has been very much to use animal models for that dose selection, and to use those animal models to also create an understanding and a relationship between biomarkers that can be accessed in the periphery, that I would call those translatable biomarkers because you can access them in humans, meaning CSF biomarkers, blood-based biomarkers, and correlate them with changes that you see in the brain on pathways and biomarkers that are in those pathways that are important for your mechanism of action. And I think that can be a very useful way of addressing this question of, is your therapeutic getting into the brain? Is it doing the intended, having the intended biologic consequence that you want? In the early days of Denali, before we embarked on even, developing our portfolio now, we actually went through and looked at all of the failed trials in neuroscience. And actually, many of them, almost more than 90% of them failed actually because they never really demonstrated adequate exposure of the drug in the brain and an effect on downstream biomarkers. Now, the question is, was this negligence? Did people not know what they were doing? No, I think this is really the result of progress. There are now biomarkers that people can look at. So before, there weren't really good imaging biomarkers. There were not easily accessible CSF biomarkers with reliable assays that could be used in the clinic. And this is an area where I do feel like there has, again, been tremendous progress.
Mm-hmm. Yeah. So you mentioned other sort of maybe genetic modifiers of the disease, and it's certainly interesting to ask whether amyloid and tau are the only ones. We know they're not. They're very strong other genetic risk factors such as apolipoprotein E gene. What is your view? Which ones are going to be worth pursuing? Which ones are you pursuing now? It maybe just also has a little bit of a background. One hears often everybody is doing amyloid trials. It's actually entirely not true. I just looked again at the 2018 data. Only 25% were targeting protein aggregates at phase 1 and phase 2, less than 50% at phase 3. I think that has shifted even more. But what are you pursuing? What is sort of something that you're really excited about?
Yeah, so I think where the genetics has really taken us in a direction that was really unexpected 10, 15 years ago was really looking at microglial biology. And you mentioned it also in work that you're doing, Tony, on understanding the immune system interaction with the brain and the nervous system. You know, I think it was really a surprise when GWAS studies showed that more than 50% of the risks in Alzheimer's disease are actually in genes that are expressed in microglia. So I think that was very much a surprise. I think the focus had very much been on the neuron and what, say, protein aggregates were doing to the neuron. But I think that that data really suggested to us that there's a lot of immunology and microglia being sort of derivatives of the immunologic system, understanding how microglia interact with neurons. So that certainly, I think, sparked a lot of interest in that area, and that's something that we're very focused on as well in our pipeline, looking at molecules, for example, TREM2 or other inflammatory pathways in microglia to understand if we can modify these pathways to have an impact on these diseases. And I think when we look at sort of broadly at where you see a lot of focus in late-stage development being on amyloid therapeutics, remember that that pathology and the genetics around amyloid preceded by quite a few years the understanding that's now emerging out of the GWAS data. But it really takes time to understand that. So going from genetic hypothesis to biologic understanding, again, is very challenging. I'll give just one example, maybe outside of the Alzheimer's disease field, but a program that we're working on is LRRK2 kinase, which is a kinase that's activated in a genetic form of Parkinson's disease. And that was actually identified as a risk in Parkinson's disease in 2004. And now we're in 2022, finally in the clinic doing studies with a clinical endpoint. So it gives a perspective on the timeline around understanding some of these biologic pathways so that we can appropriately target it. Now, we're hoping it's not going to take that long, and I think, again, with some of the progress that we've made with fluid biomarkers and imaging biomarkers, it allows us to potentially understand things better in the clinic earlier in terms of what the impact of modifying these disease risks has on endpoints that can be studied in patients.
Mm-hmm. At the Knight Initiative for Brain Resilience, where, as the name says, we're very interested in resilience, but also just learning how does the brain age, and is it even possible that, you know, during development or in early life, you become almost predisposed to, you know, certain types of outcomes or resilience, and that, you know, begs the question then, when do we start treating these diseases? What's your opinion there, and how early are you trying to intervene in your clinical trials?
Yeah, so first, I think just the idea of brain resilience is, you know, it's wonderful that you have an institute really focused on that, because I think this is going to be multifactorial. And as you look at, you know, what are risks and where are there examples where, for example, the genetics tell you that you might have a risk, for example, an autosomal dominant Alzheimer's disease mutation, but there are a few people that escape. They have other disease mutations like this ApoE Christchurch mutation where then they don't go on to have Alzheimer's disease. So what gives that sort of resilience? And I think that's something that we need to understand. And again, this is probably going to be successful, we have to target this from multiple pathways. But I think in terms of understanding when to treat, that's something that has been a big question. I think that the field has generally thought going earlier will be better, and that makes sense. I think a lot of that makes sense, one, because the problems that we're trying to address in therapeutic development right now are preventing further neurodegeneration. We're not at the point, I mean, there are programs, but I think the idea of regeneration is yet even another challenge on top of preventing further neurodegeneration. So the goal has been to really move earlier. Now, you know, if the lecanemab data is really as robust as it sounds, and I think there'll be other programs that are reading out, for example, in the anti-amyloid space in the very near term, that if we see similar results, I think there will be a body of data that suggests to us that at the stage of disease that people are intervening now, which is actually at a point where patients are already symptomatic, we can actually have an impact. And that, again, will really very much help us in how we think about drug development. I'm very much a fan of early diagnosis using biomarkers to identify patients at risk using genetics. When I was at Genentech, I led the study on the Columbia cohort using an anti-amyloid therapy and prevention. Unfortunately, that study failed, but I think the concept there is to really identify patients using genetics and risk factors to treat them before they start to have symptoms, when from a biologic perspective, I think it seems logical that you would be able to have a greater impact. But in order to do that, we really do have to understand more about the dose that we're treating and that we're having the intended biologic effect. And that's actually inherently easier in patients that are symptomatic, which is why if I see any success in the field that tells us which patient population we can do these studies in, it's a huge advance for the field and facilitates our ability to see effects on different mechanisms that we now bring into the clinic.
Wonderful. That sounds optimistic. So I know there are many other questions, and I could ask them, but I really want to open the floor now to the public. And please, any questions for Carol?
Hey, Carol. Thank you both for this very illuminating discussion. But my question: you've elected to go to the private sector in fighting these diseases, and I'm interested in your perspective on what is the best role that universities like us and initiatives like the Knight initiatives can play in the attack on these diseases, and what is the best role for the private sector like Denali to play? And are they separate roles and each should do its own thing, or are there ways for us to combine forces creatively that would give us more power than either of us has alone at this point?
Yeah, so that's a great question and one of my favorite questions. And I think that there are structural and approaches in companies that I think are very different from academia, but I think there are enormous strengths in both. And my wish is that we work all together, and we need to figure out how to do this, because these problems are huge, enormous problems, and we need all of the thinking to come together. I think where there is a structure within a private sector and in a company, that structure really allows everybody to be working towards the same goal. So it's very clear what we are trying to do, and all of the different functions and all of the sort of the thought partners that need to come together to execute on that are really working towards the same goals. Now, I have to say in academia, that can happen through collaborations and shared grants that bring people together. But I think the inherent funding mechanism doesn't necessarily foster that cross-collaboration and focus on a singular goal. But I think where I do think in academia, there is a deep understanding and focus on understanding the science that, as we've just discussed today, is just so important in understanding the mechanism of action. And again, going from the genetics to actually the pathway and how you modify that is not simple. And I think there's a lot that we can work together on understanding the science, developing biomarkers to look at these things in the clinic, developing technologies that enable this. And I think what we just need to do is find better ways to interact and collaborate on those areas. But I think that there's really a critical role for both. I would just say from a company perspective, we have always really embraced the interactions with academia, and we feel that it's really important that we are within the academic community. We're publishing data, sharing that data, because our view is that, from a competitive landscape perspective, it doesn't necessarily help us to hold data within the company where we're not sharing that data and then benefiting from interactions at scientific conferences. And so I think that that's maybe also a mindset. Not every company views it that way, but I think that that sort of openness is really important. And it's what we call sort of data in the pre-competitive space, where that data can be shared. Our goal as a company is to develop the best therapeutic target and develop it in the best way in the clinic to demonstrate an impact on patients. But a lot of that work can be shared. And in the end of the day, if it's not the best therapy for patients, it's not going to have a benefit to society. And so I think it's very important that we continue to collaborate and share data openly.
Carol, great to see you. So you you emphasized on the utility of animal models to determine the dose of treatment, so that you can ensure that the drug gets into the places at sufficient amount. So I was just wondering, much more granular question than Bill's. What about efficacy? Do you see animal models as a good way to go in terms of demonstrating efficacy, or do you think we should? Is there a lot of use for human-induced neurons? Whether those would be sort of by nature telling us more about our brain instead of an animal's brain?
Yeah, so that's a really great question on the efficacy front. And at the end of the day, I think we have to define what efficacy means. And at the end of the day, when a therapy gets approved and policymakers, payers, physicians, patients all use that therapy, the efficacy really means clinical impact and impact on health economics, right? And so that's what we think about as efficacy. But along the way, I think there are many intermediate kind of endpoints that may be important for looking at efficacy. And actually, we use that term of efficacy as like biomarker efficacy, which basically means that you're hitting the biology successfully. And that's where I do think animal models are extremely helpful. And also cellular models are very helpful in understanding, again, the relationship between dose, exposure, and intended biologic effects. So I think that animal models and other models, cellular models, absolutely need to be used to understand that level of biomarker efficacy. But then translating that to clinical efficacy, we have to actually have therapies that work in order to do that. And so I think that's the piece that we're still trying to understand.
Thanks for coming and for the conversation. It's been really stimulating and great to hear. As somebody who works on vascular disease and vascular kinds of dementia, I didn't hear much talk today yet about that. I think there's sort of two things I'm interested in your perspective on, and one is just, do you think that there is something there in terms of benefits for patients in terms of treating vascular disease? The more complicated question is, I think, how do we combat the way that diseases are studied? So, for example, people say vascular dementia is about 15 or 20% of all dementias. But if you look at people with Alzheimer's disease, about 80% of them have vascular abnormalities on brain pathology. And if you take all people with dementia, actually A beta and tau and vascular disease have this huge overlap, but they're actually about equal in terms of the number of people that are affected, and yet most dementia research has been on A beta and tau, probably because of these genetic abnormalities, which is, I think, a very good rationale. But yet, I think this is a case where there's like different fields of science that are not talking to each other. And that's really what I'm getting at, is how do we as scientists and leaders integrate fields and get people working together who are, the blind men looking at different parts of the elephant to realize that they're both looking at the same elephant.
Yeah, no, it's a great question, and I think the forum like these really bring together those ideas, and I think it's a very important concept, and I think also fits with the discussion, Tony, we had about brain resilience. And I think, when we think about what are the therapeutic goals for patients, it's to really delay the progression of disability and loss of cognitive and functional capability over time. And addressing and optimizing, for example, neurovascular health can have an enormous impact, even if you do have Alzheimer's disease, in slowing the progression of that, the manifestation of that biology. So I think that is really important. I think just in terms of, a question of why the industry has not focused on that as much, and it'd be great to get your thoughts on it, but I think, a lot of the therapeutic focus on cardiovascular health is thought to potentially translate to neurovascular health. And there's then a question of what additional mechanisms have we not addressed there that could be important for brain health. But I think even if we look at cardiovascular health, it's not a single agent, right? It's managing blood pressure, it's managing lipids, it's managing glycemic control. There are multiple factors that enable cardiovascular fitness, exercise in addition to that. So I think just as we think about brain resilience, this is going to be a multidimensional approach to really having maximum effects on patients. And I think some of the work that, Tony, you've done on looking at young plasma and benefits in older either animals or humans, that really, I think, is addressing many of those multifactorial components that can give brain resilience and help. And so I think those are all things that we need to think about. I think, again, there's maybe a question of what is tractable when we go from the scientific questions to then how do you study that in the clinic. And that's where I think some of the complexity is, and why maybe there haven't been as many programs that are specifically targeting neurovascular health for some of these brain neurodegenerative diseases.
I think. Oliver?
Oh, thank you. Really cool discussion. You mentioned a couple of times the idea of a preventive way to go about these diseases, and I think there can be no question that is a way to think about it. Thinking like 10 years ahead, what do you think we would have to have in place to actually make that happen on a population scale? I mean, currently we're paying people to get sick, essentially. So what do you think would be the biomarkers or the treatments and so on to really get to the point that we could roll this out as a preventive measurement? What do you think the elements we're still lacking and hopefully going to address?
Yeah, and it's a really great question, and something that I've certainly thought about a lot over the past decade. I think that we can be impatient and say, we've just got to prevent these diseases from happening, and we tried that. This Columbia patient study looking at anti-amyloid in this patient population, that their disease is driven by amyloid. That was an approach to do that. That obviously wasn't successful, and I think that the challenges there are going to be the challenges of starting in a prevention approach. So I think that probably the way that this is going to evolve, unless we have both the understanding of science and probably a little bit of luck, is that we start treating in symptomatic stages of disease, but that are earlier in the disease stage. We start to see effects. They may be minimal, they may not be transformative. We could even argue whether they have a health economic impact. But once we see that establishes the safety profile and the potential benefit risk profile that enables us then to move to earlier stages of disease. The earlier you go, the longer those studies are going to take. So for example, these prevention studies for Alzheimer's disease were at least 5 years long as opposed to 18 months in more symptomatic stages of disease. So you can really only do so many of those. But I think what my hope is that as we start to see some successes, it'll allow us to march earlier in the disease course. And from a health economics perspective, absolutely. That's where we want to intervene, and we want to intervene in a way that's impactful for patients, families, and health economic outcomes.
Anthony?
Thank you for this discussion. It's really been fantastic. I wanted to pick up on the points that you just raised, Carol, and maybe connect up with some of the talks that we've heard today, as well as I think one thrust of your comments, which is the role of behavioral science, these outcome measures. And I would be very interested in, you've alluded to some of the challenges here as we go earlier, but would love to hear your thoughts about how critical that is in your efforts. So you've noted perhaps Morris Water maze, maybe it's a little too blunt, maybe it's not the right readout. We know about the early reports of this new amyloid compound for MCI, maybe early AD. But as we move, perhaps to try to catch people earlier and earlier, are we using outcome variables right now, cognitive outcome variables, that are essentially too blunt? Everybody's going to be in the unimpaired, they're going to be CDR 0, they're going to be in the normal range. And there have been arguments going to the paradigm, sort of this mnemonic, similarity or discrimination task, going to other paradigms that the cognitive psychology and the cognitive neuroscience literature has suggested to us that they're stable within a population of cognitively unimpaired. There are individual differences between them, and I'm interested in the role of these kinds of discoveries in behavioral science, the role that they're being integrated into the clinical trials with the challenge that you've just noted, which is those are longer trials. What do you do with an outcome variable where everybody still remains in the same, unimpaired state? Do you see a world where we might be able at some point to be intervening early and to look at relative movement in the population where you rank, where you sit, as sort of a critical outcome variable?
Yeah, so those are also great questions, and I think maybe I'll mention sort of regulatory science now and what is substantial evidence of efficacy, which is sort of the regulatory term to get something approved. And these endpoints have to be generalizable enough and validated to represent a generalizable effect on a population that is studied and is a population that can also be defined for patients, physicians, and also health economics researchers, right? So I think that has been one of the major challenges. And how do you develop those endpoints to show those? A lot of that is in the past dependent on successful therapies that have used that endpoint. I think just in terms of whether these endpoints are good endpoints or not good endpoints, maybe I'll just give one example. The ADAS-Cog, which many here are familiar with, I think gets a bad rap by a lot of people saying that it's an insensitive endpoint. Trials have failed based on the ADAS-Cog. But I have a slightly different, and it might be a controversial opinion, but that endpoint has reliably demonstrated an effect on cholinesterase inhibitors, symptomatic therapy in Alzheimer's disease over and over again, and there's general consensus that there is a small effect that is seen across these therapies. So it's able to detect small effects. Now, the issue here is that in earlier stages of disease, that may not be the same, and I think that's one of the major issues. And I'll even just note from a regulatory perspective, the standard had been that you had to show not only an effect on cognition, but you actually also had to show an effect on function to actually get approved, which is a very high bar even in later stage disease, but you can understand why that's important from a health economics perspective, that the effect has to be meaningful enough to treat and have a health economic benefit. Otherwise, with the number of people that have Alzheimer's disease, this could really be a public health economic crisis in terms of understanding who gets access to treatment and who may benefit from treatment. But I think as we've moved to earlier stages of disease, what I have seen is that there has been a lot of flexibility from regulators now in starting to think about what are those endpoints and what in a defined patient population at a particular stage of disease an endpoint may be sufficient for approval. And I think that discussion has included looking at just, say, a cognitive endpoint or even a subset of cognitive endpoints that's important in that earlier stage of disease that may be sufficient for approval, and walking backwards from that, eventually even a biomarker, because if these patients are not symptomatic, what are you actually tracking? Are you tracking the conversion to disease? That could take a very long time. So there is openness, but we need that scientific evidence. So maybe to bring it back to some of the discussions that happened earlier today, as tools are developed that are important for looking at critical aspects of memory and thinking that would be reflective of longer-term clinical outcomes, we need to start incorporating those into natural history studies so that we can understand more about that endpoint and have the data to then support that endpoint as being a potential endpoint that could be used for approval. But really demonstrating that there's a whole science in that as well in terms of clinical outcomes and understanding of their impact. And a lot of that includes really going back to patients, caregivers, to understand whether those endpoints, do those reflect the major the problems and impact of the disease to both patients and caregivers.
Fantastic. Maybe, is there another burning question from anybody? I think we have to conclude. It's 45 minutes. I can't believe it's already passed. This was absolutely amazing, fantastic. It was really insightful, and thank you so much for coming.
Thank you,
hope
Tony.
you do that again.